Earth has already died 5 times. Not metaphorically. Not gradually. 5 times in the last 500 million years, this planet crossed a threshold where at least 75% of all species vanished within what amounts to a geological eye blink. We're standing on a graveyard that's been rewritten over and over again, and the question isn't whether it could happen again. It's what form the next reset will take. 252 million years ago, something went catastrophically wrong. The Permian Triassic extinction, what scientists call the Great Dying, erased 96% of marine life and 3/4 of everything on land. This wasn't a meteor strike or a sudden catastrophe. It was Earth slowly suffocating itself over 60,000 years. The oceans turned toxic. Oxygen levels plummeted. Temperatures spiked. And when it finally ended, the planet that emerged was fundamentally alien to everything that came before. Here's what keeps geologists awake at night. We've identified the mechanisms that triggered past extinctions, and several of them are already in motion right now. The most recent mass die-off happened 66 million years ago when a 10-kilometer asteroid punched into what's now the Yucatan Peninsula. The impact energy exceeded 10 billion Hiroshima bombs. But the rock itself didn't kill the dinosaurs. What followed did. Trillions of tons of dust and soot wrapped the planet in darkness for years. Photosynthesis stopped. Food chains collapsed from the bottom up. Global temperatures dropped by 20 to 25 degrees Celsius almost overnight. 2/3 of all species disappeared, not because they were hit directly, but because the world they evolved to inhabit simply ceased to exist. That asteroid was a freak accident. A cosmic lottery with terrible odds. But the other 4 mass extinctions, those came from Earth itself. Right now, greenhouse gas emissions are climbing towards 75 billion tons annually by 2050, nearly 50% higher than current levels. That's not a projection. That's the trajectory we're locked into based on existing infrastructure and commitments. And here's where it gets genuinely frightening. Scientists have mapped what they call climate tipping points, thresholds beyond which feedback loops take over and human intervention becomes irrelevant. The Greenland ice sheet is already shedding mass faster than models predicted a decade ago. If it crosses its tipping point, complete collapse becomes inevitable even if we stopped all emissions tomorrow. Sea levels rise 10 meters. Coastal cities drown. But that's just the opening move. Thawing permafrost in Siberia and Canada holds twice as much carbon as the entire atmosphere. As temperatures rise, frozen methane, a greenhouse gas 80 times more potent than CO2 over 20 years, erupts into the air. That warming triggers more thawing. More thawing releases more methane. The cycle feeds itself. The Amazon rainforest, often called the lungs of the planet, is approaching a different kind of threshold. Deforestation and drought are converting sections into savanna. Trees die. Rainfall decreases. More trees die. At some point, the forest can't sustain itself anymore and the entire system flips to a new state. Permanently. This isn't speculation. It's physics. Depending on how population and warming curves intersect, current models suggest 1 to 3 billion people will find themselves living in conditions that fall outside the climate envelope that has supported human civilization for the past 6,000 years. Without mass migration, 1/3 of humanity would experience average temperatures currently found only in the Sahara. Not during heat waves. As the baseline. Small island nations aren't debating this anymore. They're planning evacuations. But even if we navigate the next few centuries successfully, even if we somehow stabilize emissions and avoid the worst tipping points, Earth's habitability has an expiration date written in stellar physics. Our sun is getting brighter. Not noticeably within a human lifetime, but inexorably across geological time. 4 billion years ago, the sun emitted only 75% of its current energy output. Earth survived because our atmosphere was different, our oceans were different, the entire planetary system compensated. But the sun isn't finished evolving. In roughly 1 billion years, maybe a bit more, solar luminosity will push Earth into what's called a moist greenhouse state. Ocean water evaporates faster than it can rain back down. Water vapor is itself a greenhouse gas. More evaporation means more warming. More warming drives more evaporation. Eventually, and this is inevitable physics, not worst-case modeling, the oceans boil away entirely. Wet bulb temperatures, the measurement that combines heat and humidity to determine survivability, will exceed the human tolerance threshold everywhere on the planet. Not in deserts. Not at the equator. Everywhere. At that point, roughly 1.3 billion years from now, humans will not be able to survive outdoors on Earth under any circumstances. Our home planet will have transitioned into something resembling Venus, where surface temperatures melt lead and atmospheric pressure would crush a submarine. But we don't have 1 billion years to worry about. We have much more immediate problems. Asteroids didn't stop after the dinosaurs. Earth's orbit still crosses paths with thousands of near-Earth objects large enough to cause regional or global catastrophes. Anything bigger than 25 meters would devastate the impact zone. Anything exceeding 1 kilometer would trigger worldwide effects. A 100-kilometer impact, rare but possible, would render Earth completely inhospitable, potentially wiping out not just humanity but most complex life. We've mapped many of these objects, but not all of them. Surveys are incomplete. Some asteroids come from directions we don't monitor continuously. The object that killed the dinosaurs gave no warning. It just arrived. Then there's the threat we built ourselves. Nuclear arsenals remain large enough to trigger what's called nuclear winter. The detonations themselves would kill millions, but the real devastation comes after. Firestorms from burning cities inject massive quantities of soot into the stratosphere. That soot blocks sunlight for years, maybe a decade. Global temperatures plummet. Photosynthesis crashes. Crops fail worldwide. Recent modeling suggests a full-scale exchange between major powers would reduce global food production by 90% within a few years. 5 billion people would die from starvation, not radiation. Even a regional nuclear war between smaller nations like India and Pakistan could cut food production in half and kill 2 billion through famine alone. These aren't abstract scenarios. These are weapons that exist right now, maintained on hair trigger alert, subject to human decision-making under crisis conditions. Beneath Yellowstone National Park sits a supervolcanic system that's erupted catastrophically 3 times in the past 2 million years. The last major event occurred 640,000 years ago. If it erupts again at similar scale, global temperatures would drop by 4 degrees Celsius on average, 7 degrees across land, and more than 10 degrees across central North America. Ash would blanket continents. Growing seasons would collapse. The effects would persist for decades. The probability of this happening soon is extremely low. But extremely low isn't zero. And we have no way to prevent it. While these dramatic scenarios capture attention, a slower catastrophe is already unfolding in the oceans. About 25% of human CO2 emissions dissolve directly into seawater. That might sound beneficial, like the ocean is helping clean the atmosphere. But it's not. That dissolved CO2 forms carbonic acid, fundamentally altering ocean chemistry. Coral reefs, which support roughly 25% of all marine species despite covering less than 1% of the ocean floor, require specific pH levels to build their calcium carbonate skeletons. A 20% increase in atmospheric CO2, which could happen within 2 decades at current rates, would make it impossible for many coral species to grow. Some would become functionally extinct within our lifetimes. When corals die, the species that depend on them collapse. Fish populations crash. Coastal communities lose their protein sources. Storm barriers disappear. The cascade moves up the food chain, cutting through marine ecosystems that have sustained human civilizations for millennia. And here's the truly insidious part about ocean acidification. Unlike temperature increases, which we could theoretically reverse by removing CO2 from the atmosphere, ocean chemistry changes persist for thousands of years. Even if we stopped all emissions today, the acid already in the water would continue degrading marine ecosystems for centuries. Earth's protective magnetic field, the invisible shield that deflects solar radiation and prevents our atmosphere from being stripped away, isn't permanent. The field reverses polarity at irregular intervals, averaging every few 100,000 years. During these reversals, which can take several thousand years to complete, the magnetic field weakens dramatically but doesn't disappear entirely. Around 41,000 years ago, during the Lost Champ excursion, Earth's magnetic field dropped to roughly 5% of its current strength. Radiation exposure increased. Ice cores and tree rings preserve evidence of this event. Some research suggests that during past reversals, solar wind actually stripped oxygen from our atmosphere because the weakened magnetic field couldn't protect it. Species may have died from asphyxiation during these periods. We're not due for a reversal imminently, but the possibility exists on timescales relevant to human civilization. And unlike asteroid impacts, we'd have no way to prevent it. What makes all of this particularly unsettling is how interconnected these systems are. Earth doesn't operate as isolated components that fail independently. Everything links to everything else. When one system destabilizes, it stresses others. Those systems push against their own thresholds. Partial collapses trigger cascading failures. Species don't exist in isolation. They form networks where each organism supports others through pollination, predation, decomposition, nutrient cycling. When populations crash, those connections break. Ecosystems lose resilience. What looks like a local problem, the extinction of one species in one region, ripples outward in ways we're only beginning to map. The geological record shows that Earth has recovered from extreme conditions before, but those recoveries required millions of years and produced completely different biospheres. The world that emerged after the Permian extinction bore little resemblance to what came before. Human civilization operates on timescales of decades to centuries, not geological epochs. We can't wait millions of years for ecosystems to rebuild. We need the planet to remain habitable now, and continuously, for as long as our species exists. That's a vastly different challenge than what Earth's deep history teaches us about recovery. So when we ask if Earth could become uninhabitable again, we're really asking several questions simultaneously. Could it happen suddenly, like the asteroid that ended the Cretaceous? Could it happen gradually, like the Great Dying? Could we trigger it ourselves? And perhaps most critically, on what timescale are we measuring? The answer to all of these is yes, with very different probabilities and very different timelines. But the mechanisms are real, The precedents exist in rock layers we can touch, and several of them are already in motion. What happens next depends on choices we make in the immediate future, decisions that will echo across geological time whether we intend them to or not. Human Script continues exploring exactly how these mechanisms work, what the warning signs look like, and whether the trajectory we're on can still be altered. The choices we're making right now aren't abstract policy decisions that might matter someday. They're determining whether feedback loops that have already started will accelerate past points of no return or whether we can still pull them back from those thresholds. Start with the Amazon rainforest. For millions of years, it's functioned as Earth's primary terrestrial carbon sink, absorbing massive amounts of CO2 from the atmosphere. The forest generates roughly half of its own rainfall through a process called evapotranspiration, where trees release water vapor that forms clouds, which then produce rain that falls back onto the forest. It's a self-sustaining cycle. But deforestation and rising temperatures are pushing the system toward collapse. When you clear trees, you reduce evapotranspiration. Less moisture in the air means less rainfall. Drier conditions make the remaining forest more vulnerable to fires. Those fires release stored carbon and kill more trees. Fewer trees mean even less rainfall. The cycle reinforces itself. Scientists estimate that if 20 to 25% of the Amazon is destroyed, the entire system could flip into a fundamentally different state. Instead of rainforest, you'd get savanna, grassland with scattered trees that stores far less carbon and produces far less rainfall. We're currently sitting at roughly 17% deforestation. The margin we're working with isn't comfortable. And once that flip occurs, reversing it isn't simply a matter of replanting trees. The regional climate will have changed. The soil chemistry will have shifted. You can't just restore what was lost because the conditions that allowed it to exist in the first place no longer exist. This same pattern appears in Arctic permafrost. Frozen soil across Siberia, Alaska, and Canada contains roughly 1,500 billion tons of carbon, about twice what's currently in Earth's atmosphere. As temperatures rise, permafrost thaws. Microbes that were dormant in frozen soil become active and start breaking down organic matter. That decomposition releases carbon dioxide and methane. Those greenhouse gases warm the atmosphere further. More permafrost thaws. More carbon gets released. The process feeds itself. What makes permafrost particularly dangerous is the methane component. Methane is roughly 80 times more potent than CO2 as a greenhouse gas over a 20-year timescale. Some permafrost regions contain massive deposits of methane hydrates, frozen methane trapped in ice-like structures. When those destabilize and release their methane into the atmosphere, the warming effect is immediate and severe. We're already seeing evidence of this happening. Large craters have appeared in Siberia where underground methane explosions blew through the surface. Methane concentrations in the Arctic atmosphere are measurably increasing. The terrifying aspect of these feedback loops is their irreversibility on human timescales. Once permafrost carbon enters the atmosphere, it doesn't go back into the ground. Once the Amazon transitions to savanna, the carbon stored in billions of trees is gone. These aren't temporary disruptions that nature can smooth out over a few decades. They represent permanent shifts in how Earth's carbon cycle functions. Ocean currents present another system approaching critical thresholds. The Atlantic Meridional Overturning circulation, which includes the Gulf Stream, transports warm water from the tropics toward the North Atlantic. As that water cools and becomes denser, it sinks and flows back south along the ocean floor. This circulation redistributes heat across the planet and influences weather patterns for billions of people. Greenland's ice sheet is melting at accelerating rates. That meltwater, being freshwater, is less dense than seawater. When massive amounts of freshwater pour into the North Atlantic, they disrupt the density-driven sinking that keeps the circulation running. Models show the AMOC has already weakened by roughly 15% since the mid-20th century. If the AMOC collapses entirely, which some researchers suggest could happen within this century, the consequences cascade globally. Europe would experience significantly colder temperatures despite overall global warming. Monsoon patterns in Africa and Asia would shift, affecting water availability for billions of people. Sea levels along the eastern coast of North America would rise faster than the global average because the Gulf Stream currently pulls water away from the shore. Marine ecosystems dependent on nutrient upwelling driven by the circulation would collapse. And here's what makes this particularly unsettling. These systems don't provide clear warning signs before they tip. They appear relatively stable, changing gradually, until suddenly they cross a threshold and flip into a completely different state within years or decades. Ice core data from Greenland shows that past climate shifts, triggered by AMOC changes, occurred within as little as 3 years. The ocean current that had been running for thousands of years simply stopped. Temperatures in the North Atlantic region dropped by several degrees in less than a decade. You're probably thinking that surely we'd see these catastrophic shifts coming and take action before they happen. But that assumption doesn't match how these systems actually behave. Tipping points, by definition, are thresholds you don't fully recognize until you've crossed them. The early warning signs look like normal variability. Slightly warmer years, a bit more ice melt, some unusual weather patterns. Nothing that screams planetary emergency until the system is already past the point where intervention could prevent the flip. Climate models can identify potential tipping points, but they can't tell us exactly where those thresholds sit or how close we are to crossing them. The models work with approximations, simplified representations of enormously complex systems. They might tell us an ice sheet could collapse if warming reaches 2 degrees Celsius, but the actual threshold might be 1.8 degrees or 2.3 degrees. We're conducting a real-time experiment on the only planet we have, and we won't know the results until we're living through them. Multiple tipping points interacting with each other create scenarios that become almost impossible to model accurately. If the Amazon transitions to savanna while permafrost releases massive methane pulses while the AMOC slows while ice sheets destabilize, those effects don't simply add together. They multiply. Each amplifies the others. The warming from methane accelerates ice melt. Ice sheet collapse disrupts ocean circulation. Circulation changes alter rainfall patterns that stress the Amazon further. The entire Earth system enters a state it hasn't experienced in millions of years, potentially tens of millions. This is what researchers mean by Hothouse Earth. Not just a warmer planet, but one where human activities have triggered feedback loops that continue driving temperatures higher regardless of what we do afterward. Once certain thresholds are crossed, even if we stopped all emissions immediately, the planet would keep warming for centuries because the feedbacks we've activated would continue operating on their own momentum. How much time do we have before crossing these points? That's the question everyone wants answered with precision, and it's the question science can't definitively answer. Different tipping points have different timescales. Some ice sheet dynamics operate over centuries. Some permafrost thaw happens over decades. Some ocean current changes could occur within years. The uncomfortable truth is that we're already seeing signs that several of these systems are destabilizing faster than earlier models predicted. Greenland's ice sheet is losing mass at rates that weren't expected until mid-century. The Amazon experienced severe droughts in 2005, 2010, and 2015, each time shifting from carbon sink to carbon source as dying trees released more CO2 than growing trees absorbed. Arctic sea ice is declining faster than nearly all models projected. These aren't speculative future scenarios. They're measurements of what's happening right now. The margin between our current trajectory and catastrophic tipping points isn't measured in comfortable centuries. It's measured in decades, possibly less for some systems. And every fraction of a degree of additional warming increases the probability that we'll cross thresholds we can't uncross. This is why the difference between 1.5 degrees and 2 degrees of warming isn't just a number on a thermometer. It's the difference between climate change as a severe challenge we can adapt to and climate change as an existential threat that fundamentally alters whether Earth remains hospitable for human civilization. What happens when we examine the specific mechanisms that could push us across those thresholds? The mechanisms operate on principles that sound almost absurdly simple until you understand their implications. Take ice sheets. White surfaces reflect sunlight back into space. Dark surfaces absorb it. When ice melts, it exposes darker land or ocean beneath. That darker surface absorbs more heat, which melts more ice, which exposes more dark surface. The physics is straightforward. The consequences are anything but. Greenland's ice sheet contains enough frozen water to raise global sea levels by about 7 meters. Antarctica holds enough for 60 meters. These aren't theoretical numbers. They're measurements of actual ice sitting on actual continents. The question isn't whether that ice contains enough water to reshape every coastline on Earth. It does. The question is how fast it melts and whether we can stop the process once it starts accelerating. Ice doesn't melt uniformly. It develops what glaciologists call tipping points, where small changes in temperature produce disproportionately large changes in melting rate. An ice sheet sitting at -10 degrees needs significant warming before it starts losing mass. But an ice sheet at -1 degree is fundamentally unstable. A single degree of additional warming doesn't just melt 10% more ice. It can double or triple the melt rate because it pushes the entire system across a physical threshold. Current observations show Greenland losing about 280 billion tons of ice per year. That's already accelerating sea level rise. But here's what makes this a tipping point rather than just a trend. As the ice sheet thins, its surface elevation drops. Lower elevation means warmer air temperatures. Warmer temperatures mean faster melting. Faster melting means more thinning. The loop reinforces itself. Eventually, the ice sheet reaches a geometry where it can't maintain its own mass regardless of what happens with emissions. It's committed to collapse even if we somehow froze atmospheric temperatures at current levels. Antarctica presents an even more complex problem. Parts of the West Antarctic ice sheet rest on bedrock that's below sea level. The ice extends out over the ocean in massive floating shelves. These shelves act like buttresses, holding back the land-based ice behind them. When ocean water warms, it melts these shelves from below. As the shelves thin and eventually break apart, they stop restraining the land ice. Glaciers that were moving toward the ocean at a few meters per year suddenly accelerate to hundreds of meters per year. The ice doesn't melt. It slides into the ocean and melts there. Marine-based ice sheets have a particularly nasty characteristic. Once they start retreating, the process can become unstoppable even without additional warming. As the ice front pulls back, it moves into deeper water where the ice is thicker and more vulnerable to ocean melting. The retreat accelerates. This is called marine ice sheet instability, and we're seeing evidence it's already begun in parts of Antarctica. The Thwaites Glacier, roughly the size of Florida, appears to be in the early stages of this kind of collapse. If it goes, it could destabilize enough surrounding ice to raise sea levels by 3 meters. 3 meters doesn't sound catastrophic until you map it onto actual coastlines. Miami goes underwater. So do significant portions of New York, Shanghai, Mumbai, and hundreds of other cities housing hundreds of millions of people. But the real problem isn't the final sea level. It's the rate of rise. Human societies can theoretically adapt to 3 meters of sea level rise if it happens over 1,000 years. We absolutely cannot adapt if it happens over a century. And once these ice sheet dynamics kick in, century-scale collapse becomes possible. Now layer permafrost on top of this. The Arctic contains roughly 1,400 billion tons of carbon locked in frozen soil. That's more than twice the amount currently in Earth's atmosphere. As temperatures rise, this frozen ground thaws. Microbes that have been dormant for thousands of years wake up and start consuming the organic matter. Their metabolism releases carbon dioxide and methane. The released greenhouse gases warm the atmosphere further. More permafrost thaws. More carbon releases. Another reinforcing loop. The methane component makes this particularly dangerous. Methane traps about 25 times more heat than carbon dioxide over a century-long timescale. Over the first 2 decades after release, it's roughly 80 times more potent. When permafrost thaws in waterlogged conditions, microbes produce methane instead of carbon dioxide. Arctic lakes are already bubbling with methane from thawing lake beds. Methane concentrations in the atmosphere are rising faster than models predicted. We're watching the early stages of this feedback activate in real time. But here's where multiple tipping points interacting create scenarios that become genuinely terrifying. Warming from greenhouse gas emissions melts ice sheets. Ice sheet collapse weakens ocean circulation. Weakened circulation disrupts the jet stream. Jet stream disruption changes rainfall patterns. Changed rainfall stresses the Amazon rainforest. A stressed Amazon releases carbon instead of absorbing it. Released carbon accelerates warming. Accelerated warming melts more ice and thaws more permafrost. Every system pushes on every other system. The Atlantic Meridional Overturning Circulation, the AMOC, provides a clear example of how quickly these changes can occur once triggered. This current system moves warm water from the tropics toward the North Atlantic. As it cools, the water becomes denser and sinks, then flows back south at depth. This circulation redistributes enormous amounts of heat around the planet. It's why Western Europe has relatively mild winters despite being at the same latitude as northern Canada. Melting ice sheets dump massive quantities of fresh water into the North Atlantic. Fresh water is less dense than salt water. It doesn't sink as readily. As the surface water freshens, the circulation weakens. Climate records from ice cores show this circulation has shut down completely in the past. When it did, temperatures in parts of Europe dropped by 5 to 10 degrees within decades. Not centuries. Decades. The system has 2 stable states, on and off, with not much in between. Current measurements show it's already slowing by about 15% compared to mid-20th century levels. We don't know where the threshold sits. We just know we're pushing toward it. Ocean acidification operates on a different timescale but with equally fundamental impacts. The ocean has absorbed roughly 25% of all the carbon dioxide humans have emitted. This absorption has slowed atmospheric warming, but at a cost. When CO2 dissolves in seawater, it forms carbonic acid. Ocean pH has already dropped by 0.1 units since pre-industrial times. That might not sound significant until you understand pH is a logarithmic scale. A 0.1 decrease represents a 30% increase in acidity. Calcium carbonate, the mineral that forms coral skeletons and shellfish shells, dissolves more readily in acidic water. Organisms that build these structures have to expend more energy to maintain them. At some threshold of acidity, building calcium carbonate structures becomes energetically impossible. Corals can't grow. Shellfish can't form shells. Tiny plankton with calcium carbonate tests can't maintain their bodies. These aren't peripheral species. They're foundational to marine food webs. When they collapse, everything that depends on them collapses in sequence. Coral reefs support about 25% of all marine species despite covering less than 1% of the ocean floor. They're already experiencing mass bleaching events as water temperatures spike during heat waves. Acidification adds a second stressor. Corals trying to recover from bleaching find themselves unable to rebuild their calcium carbonate skeletons in increasingly acidic water. The combination of heat stress and acidification is pushing reef systems toward functional extinction within decades in many regions. Once the reefs die, they don't come back on any timescale relevant to human civilization. Reef ecosystems take thousands of years to develop. Each of these mechanisms has its own threshold, its own timeline, its own internal dynamics. Ice sheets respond over decades to centuries. Ocean circulation can flip in years to decades. Permafrost thaw operates over decades to centuries. Acidification is already affecting organisms and will continue worsening for centuries even if emissions stop today. The forest-to-savanna transition in the Amazon could happen within 50 years of crossing the threshold. We're simultaneously conducting experiments on all these systems, and we won't know which threshold we've crossed until we're past it. The truly destabilizing realization is that these aren't separate problems we can address sequentially. They're interconnected components of a single planetary system. You can't solve ice sheet stability without addressing ocean warming. You can't address ocean warming without dealing with atmospheric greenhouse gases. You can't stabilize greenhouse gases while permafrost releases accelerate. You can't prevent permafrost thaw without limiting overall warming. Every intervention requires addressing the whole system simultaneously. And we're running these experiments with incomplete knowledge on systems we only partially understand. How close is Greenland to irreversible collapse? We have estimates ranging from decades to centuries depending on emission scenarios, but the range itself shows how much uncertainty remains. What's the threshold for AMOC shutdown? Models suggest somewhere between 1.5 and 3 degrees of warming, but that's a massive range when we're already past 1 degree. At what point does the Amazon tip? Studies suggest 20 to 25% deforestation combined with continued warming, but we're already at 17% deforestation and temperatures keep rising. The mechanisms themselves are well understood. The thresholds remain frustratingly uncertain. And the consequences of crossing them unfold across timescales that make political action nearly impossible until it's too late. But even these physical tipping points don't capture the full scope of how Earth could become uninhabitable. There are threats that don't emerge from climate feedbacks at all. Asteroid impacts offer a different category of existential threat entirely. Unlike climate feedbacks that unfold over decades to centuries, an asteroid large enough to trigger mass extinction arrives without warning on human timescales. You get hours to days of advance notice if detection systems work perfectly. Then physics takes over. The Chicxulub impact 66 million years ago released energy equivalent to about 10 billion Hiroshima bombs. The asteroid was roughly 10 kilometers across. When it hit, it vaporized instantly, along with a significant portion of Earth's crust at the impact site. The explosion created a crater over 180 kilometers wide and threw trillions of tons of material into the atmosphere and beyond. Some of it reached escape velocity and left Earth entirely. The rest came back down. Here's what that re-entry looked like. Millions of fragments, some the size of pebbles, others boulder-sized, fell back through the atmosphere simultaneously across the entire planet. Each one heated to incandescence from atmospheric friction. The sky filled with shooting stars. Not a few. Millions. The radiant heat was intense enough to ignite vegetation on multiple continents. Forests that had existed for millions of years burned in hours. The thermal pulse was just the opening act. The real damage came from what happened next. All that ejected material, the dust and aerosols, blocked sunlight for months to years depending on latitude. Photosynthesis stopped. Temperatures plunged. The impact winter killed more species than the impact itself. Food chains collapsed from the bottom up. Herbivores starved. Then carnivores. The organisms that survived were small, could hibernate, or had access to food sources that didn't depend on active photosynthesis. Could it happen again? Absolutely. The question isn't if, it's when. Earth gets hit by space rocks constantly. Most are small enough to burn up in the atmosphere. The dangerous ones, objects over 1 kilometer across, arrive much less frequently. Current estimates suggest a civilization-threatening impact occurs roughly once every few million years. That sounds comfortably distant until you realize how probability actually works. A 1 in a million year event has a 1 in a million chance of happening in any given year. Including this one. The odds don't care that the last big impact was 66 million years ago. Each year carries the same tiny but non-zero probability. Over human timescales of decades to centuries, the cumulative risk becomes significant. NASA and other space agencies track near-Earth objects specifically because of this threat. They've cataloged most of the kilometer-plus asteroids that cross Earth's orbit. Most. Not all. And the detection systems only work for objects we can see coming. A comet from the outer solar system, something on a trajectory that brings it close to Earth for the first time, might give us months of warning. Maybe weeks. Possibly less. What happens if we detect an incoming impactor with sufficient warning? The answer depends entirely on how much time we have. Years of advance notice opens up options. You could launch a mission to deflect the asteroid, change its trajectory slightly so it misses Earth entirely. A small change applied early enough becomes a large displacement by the time it reaches Earth's orbit. This isn't science fiction. The physics works. We've even tested it. But it requires years of preparation and assumes the asteroid is detected early enough. With less warning, options narrow dramatically. Months instead of years means you're looking at more desperate measures. Nuclear weapons become the go-to solution not because they vaporize the asteroid, they don't, but because the explosion might fragment it or alter its trajectory enough to matter. Whether that actually works depends on the asteroid's composition, its trajectory, how much time remains. The uncertainty is substantial. Days of warning. You're not stopping it. The best you can do is predict where it's going to hit and evacuate if possible. But evacuating from an impact that's going to trigger global climate disruption doesn't really solve the problem. You're not escaping the aftermath. The impact itself might be survivable depending on where you are relative to ground zero. The impact winter that follows is the real threat. When photosynthesis stops for months, food production stops. Modern agriculture depends entirely on annual crops that need continuous growing seasons. There's no hibernating through a multi-year winter. Food stores run out in months. Then people start dying. Not from the impact. From starvation. The geologic record shows this pattern repeating. The 5 major mass extinctions in Earth's history had different causes, but several involved rapid climate disruption that collapsed food chains. The Permian Triassic extinction 252 million years ago killed roughly 96% of marine species and 70% of terrestrial vertebrates. The trigger wasn't an asteroid. It was massive volcanic eruptions in what's now Siberia. The Siberian Traps eruptions released enormous volumes of carbon dioxide and sulfur dioxide over hundreds of thousands of years. That's the timescale that matters. Not the eruption itself, but the sustained release of gases that altered global climate faster than ecosystems could adapt. Temperatures spiked. Ocean chemistry changed. Oxygen levels dropped. Species died in waves as each environmental shift cascaded through interconnected food webs. Recovery took millions of years. Supervolcanic eruptions represent another low-probability, high-consequence threat. Yellowstone is the famous example. Beneath Yellowstone National Park sits a magma chamber roughly 55 kilometers long and 20 kilometers wide. It's been erupting on a roughly 600,000-year cycle. The last eruption was 640,000 years ago. The math makes people nervous. If Yellowstone erupted at the scale of its previous super-eruptions, the immediate devastation would be regional. Ash would blanket much of North America. But the global effects would come from aerosols injected into the stratosphere. Sulfur dioxide converts to sulfuric acid droplets that reflect sunlight. Global temperatures would drop by several degrees for years. Growing seasons would shorten. Crop failures would be widespread. Here's the thing though. The probability of a Yellowstone supereruption in any given year is about 1 in 730,000. It's possible. It's not imminent. And geologists monitor the system continuously. Magma movements large enough to precede a supereruption would show up as earthquake swarms, ground deformation, changes in hydrothermal activity. We'd likely have some warning. But warning doesn't mean prevention. You can't stop a volcano from erupting. You can evacuate people from the immediate area. You can't evacuate from global climate effects. Once again, you're facing a scenario where the trigger event might be survivable, but the aftermath determines whether civilization continues. Nuclear war sits in a different category because unlike asteroids or volcanoes, it's entirely preventable and entirely anthropogenic. The threat isn't from nature. It's from us. During the Cold War, both the United States and Soviet Union built arsenals capable of destroying each other multiple times over. The doctrine was mutually assured destruction. Neither side could win, so neither side would start a war. That logic held. Barely. There were close calls. Miscommunications. False alarms. Incidents where individuals had to make decisions about whether radar signatures indicated incoming missiles or were technical glitches. The fact that we're here means they chose correctly. But it was close. Uncomfortably close. Current arsenals are smaller than Cold War peaks but still massive. The United States and Russia each maintain thousands of warheads. China, France, the United Kingdom, Pakistan, India, Israel, and North Korea also have nuclear weapons. The scenarios for how nuclear war starts vary. Intentional first strike. Miscalculation during a crisis. Accidental launch. Terrorist acquisition of weapons. Each pathway has different probabilities, but none are zero. If nuclear war happens at scale, the immediate deaths from blasts and radiation would be catastrophic. Hundreds of millions dead within hours to days. But that's not the existential threat. Nuclear winter is the existential threat. The firestorms triggered by nuclear explosions in cities would inject massive amounts of soot into the stratosphere. Black carbon particles absorb sunlight, heating the stratosphere while blocking light from reaching the surface. Climate models show that a large-scale nuclear exchange between the United States and Russia could drop global temperatures by 5 to 8 degrees Celsius. The cooling would last a decade or more. Agriculture would collapse. A study from 2022 estimated that a US-Russia nuclear war would reduce global calorie production by 90% within a few years. 5 billion people would die from famine. Not from the war itself. From starvation in the years after. Even smaller nuclear exchanges produce catastrophic results. A war between India and Pakistan involving roughly 100 weapons would inject enough soot to drop global temperatures and reduce crop yields worldwide. 2 billion people could face starvation. These aren't marginal effects. They're existential threats to civilization that cascade from relatively small initial triggers. What makes nuclear winter particularly terrifying is that it's entirely avoidable. Asteroids and volcanoes are natural hazards. We can't prevent them. Nuclear war is a choice. A choice that remains possible as long as the weapons exist. Every year we don't dismantle these arsenals is another year we're betting on continued rationality and functional command and control systems. It's a bet we've won so far. But the stakes keep compounding. Each of these threats operates on different timescales with different probabilities. Asteroids are random. Supervolcanoes have cycles but with huge uncertainties. Nuclear war depends on human decisions. Climate feedbacks are already in motion. But they all share one characteristic. Once triggered, they're extremely difficult or impossible to reverse on timescales that matter to civilization. The probability calculations don't provide much comfort when you're talking about events that erase civilizations. Here's what keeps risk analysts awake. We're not just dealing with individual threats operating in isolation. We're dealing with interconnected systems where one failure can trigger cascades across multiple domains. Take the current biodiversity crisis. Species extinction rates are running somewhere between 100 and 1,000 times higher than background rates. That's the natural rate at which species would disappear without human influence. Some estimates push it higher. 1,000 to 10,000 times background. The numbers vary depending on methodology and which taxonomic groups you're measuring, but the direction is consistent. We're losing species faster than natural replacement rates. Whether this constitutes a sixth mass extinction is debated. Less than 0.1% of known species have gone extinct in the last 500 years. That's nowhere near the 75% threshold that defines mass extinctions in the geological record. But the trajectory matters more than the current total. Vertebrate species loss over the last century would have taken 800 to 10,000 years under natural conditions. We've compressed millennia of extinction into decades. Why does this matter for habitability? Because ecosystems aren't collections of independent parts. They're networks. Species interact in ways that produce clean air, clean water, healthy soils, stable climate regulation. When one species disappears or its population crashes, others are affected. The ecosystem functions differently. Sometimes it degrades. Sometimes it collapses entirely. Coral reefs demonstrate this perfectly. They cover less than 1% of the ocean floor but support roughly 25% of marine species. Ocean acidification is dissolving the calcium carbonate structures that corals build. A 20% increase in atmospheric carbon dioxide above current levels could make it impossible for many corals to maintain their skeletons. That increase could happen within 2 decades. When corals die, reef ecosystems collapse. Fish populations crash. Coastal communities lose food security, storm protection, tourism revenue. But it doesn't stop there. Reef degradation affects ocean chemistry, nutrient cycling, carbon storage. The impacts cascade through marine food webs starting with larvae and shellfish, then moving up to larger predators and eventually affecting terrestrial systems that depend on ocean productivity. This is what makes the biodiversity crisis different from an asteroid impact. It's not a single catastrophic event. It's a slow unraveling of the systems that maintain habitability. And unlike asteroids, it's entirely driven by human activity. Here's where it gets uncomfortable. The same industrial processes driving biodiversity loss are also destabilizing the climate, acidifying the oceans, depleting freshwater, degrading soils, and spreading pollutants. These aren't separate problems. They're interconnected manifestations of how modern civilization extracts resources and disposes of waste. Climate change alone could render large portions of Earth uninhabitable for humans. Not the entire planet. Regional uninhabitability. Depending on population growth and warming scenarios, 1 to 3 billion people could end up living outside the climate conditions that have supported human civilization for the past 6,000 years. Without migration, a third of the global population would experience average temperatures currently found in the Sahara. The mechanism is straightforward. Humans can't survive sustained exposure to wet bulb temperatures above 35 degrees Celsius. That's the point where the body can no longer cool itself through sweating. You die from hyperthermia regardless of hydration or shade. Parts of the Middle East, South Asia, and other tropical regions already approach this threshold during heat waves. As global temperatures rise, these conditions become more frequent and widespread. But even before you hit lethal temperature thresholds, you get agricultural collapse. Crop yields drop. Water sources dry up. Infrastructure fails under heat stress. People move or they die. The refugee flows we've seen from recent conflicts and droughts are tiny compared to what climate displacement could produce. We're talking hundreds of millions of people forced to migrate because their home regions can no longer support human life. This creates a nasty feedback loop. Climate refugees put pressure on regions that are still habitable. Resource competition intensifies. Political instability spreads. The systems that might coordinate global responses start breaking down precisely when coordination becomes most critical. Now layer in the other threats. Ocean acidification continues regardless of temperature. Biodiversity loss accelerates as climate zones shift faster than species can migrate. Soil degradation reduces agricultural capacity exactly when you need to feed more people with less arable land. Freshwater becomes scarcer as glaciers melt, precipitation patterns change, and aquifers deplete. These aren't distant future scenarios. They're happening now at measurable rates. The question isn't whether these trends will make parts of Earth uninhabitable. They already are. The question is how far it goes and how fast. The Hothouse Earth scenario represents the extreme end. It's a state where positive feedback loops drive temperatures beyond human control. Ice sheets collapse, raising sea levels 10 meters. Permafrost thaws, releasing massive methane pulses that supercharge warming. The Amazon transitions from rainforest to savanna, eliminating a major carbon sink. Warm water corals disappear entirely. Each of these represents a tipping point, a threshold beyond which the system doesn't return to its previous state even if you remove the initial forcing. Once the Greenland ice sheet passes a certain melting point, it keeps melting regardless of future emissions. Once permafrost starts thawing at scale, the methane release becomes self-sustaining. Once the Amazon forest cover drops below a critical percentage, the regional climate shifts and prevents forest recovery. Climate models suggest we're approaching several of these tipping points simultaneously. The exact thresholds are uncertain. Could be 1.5 degrees of warming. Could be 2. Could be 2.5. But the risk increases with every tenth of a degree. And unlike gradual warming, tipping points are nonlinear. The system looks stable until suddenly it isn't. What makes this genuinely terrifying is the timescale mismatch. The industrial processes driving these changes operate on timescales of decades. The climate system responds on timescales of centuries to millennia. Which means the warming we've already committed to hasn't fully materialized yet. Even if emissions stop tomorrow, temperatures would keep rising for decades as the ocean and atmosphere equilibrate. That's the gap where civilization has to operate. We're making decisions now that determine climate outcomes centuries from now, but we're using political and economic systems designed for quarterly earnings reports and election cycles. The disconnect is profound. Earth's magnetic field adds another layer of vulnerability. The field has been weakening for the past 2,000 years. It's currently about 10% weaker than it was when measurements began. This isn't necessarily a precursor to reversal, but it does mean less protection from solar radiation and cosmic rays. During the Lost Champ excursion 41,000 years ago, the field dropped to about 5% of current strength. Radiation exposure increased dramatically. Some research suggests atmospheric oxygen decreased because the solar wind stripped away ozone and oxygen that normally would have been protected. Species may have died from asphyxiation during these events. The field hasn't disappeared during reversals in the past several million years. It weakens significantly but doesn't go to zero. The magnetosphere and atmosphere continue providing protection. But there would be increased radiation at the surface. Electronics would be more vulnerable. Satellite systems could fail. Power grids could experience disruptions. For modern technological civilization, a magnetic reversal wouldn't be an extinction event, but it could be severely destabilizing. And if it happened while we're dealing with climate change, biodiversity loss, and resource depletion, the combined stress could push systems past their breaking points. The far future offers no escape. Around 1 billion years from now, the sun's increasing luminosity will push Earth into a moist greenhouse state. Water vapor in the atmosphere will trap heat more efficiently. Ocean evaporation accelerates. Eventually the oceans boil away entirely. Wet bulb temperatures exceed the hyperthermia limit everywhere. Humans couldn't survive outdoors anywhere on the planet. Before that, around 250 million years from now, continental drift will form a new supercontinent. The interior regions will be unbearably hot. Daytime temperatures could exceed 70 degrees Celsius. Combined with elevated carbon dioxide from enhanced volcanic activity, most of the landmass becomes uninhabitable for mammals. These timescales are so long they feel abstract. Hundreds of millions of years. Billions of years. But they establish something important. Earth's habitability is temporary. Eventually, through natural processes alone, this planet will stop supporting complex life. The sun will see to that. The only question is whether we make it uninhabitable on much shorter timescales through our own actions. And right now, that's exactly the trajectory we're on. Here's what makes this different from past extinction events. When the asteroid hit 66 million years ago, it was a sudden shock. Devastating, yes. But localized in time. The biosphere could begin recovering the moment conditions stabilized. The Permian extinction unfolded over tens of thousands of years. Brutal, but still a discrete event with a beginning and end. What we're doing now has no clear endpoint. We're not experiencing a single catastrophic moment. We're creating sustained pressure across multiple systems simultaneously. Climate warming, ocean acidification, habitat destruction, chemical pollution, biodiversity collapse. Each one alone would stress the biosphere. Together, they create conditions Earth hasn't seen in the entire history of complex life. The pace matters more than almost anything else. Evolution works through random mutation and natural selection over many generations. Species adapt when there's time for beneficial traits to spread through populations. When environments change faster than generation times allow, adaptation becomes impossible. You can't evolve your way out of a crisis that unfolds in decades when your species takes years to reach reproductive maturity. Current extinction rates sit somewhere between 100 and 1,000 times higher than the background rate. Some estimates push even higher. The number of species that have gone extinct in the last century would have taken between 800 and 10,000 years to disappear naturally. We've compressed millennia of extinction into a single human lifetime. Less than 0.1% of known species have gone extinct in the past 500 years. That sounds reassuring until you understand what it means. We're still in the early stages. The full impact of habitat destruction, climate change, and ecosystem disruption hasn't manifested yet. There's a lag between cause and effect. Species pushed past their survival threshold don't disappear immediately. They decline over decades as populations fragment, genetic diversity drops, and reproductive rates fall. This creates what biologists call extinction debt. Species that are functionally extinct but haven't physically disappeared yet. Walking dead. The collapse is already locked in. We just haven't seen the bodies yet. Ocean acidification illustrates the problem perfectly. Nearly 25% of human-produced carbon dioxide gets absorbed by the ocean. This seems helpful at first. Less CO2 in the atmosphere means less warming. But the ocean isn't a permanent storage solution. It's a chemical system with limits. When CO2 dissolves in seawater, it forms carbonic acid. Ocean pH has already dropped by 0.1 units since pre-industrial times. That might not sound significant. But pH is logarithmic. 0.1 units represents a 30% increase in acidity. And we're just getting started. Projections suggest another 20% increase in atmospheric CO2 could occur within 2 decades. At that point, corals lose the ability to build their calcium carbonate skeletons. Some species become functionally extinct within our lifetime. When corals go, everything that depends on reef ecosystems follows. Fish, crustaceans, mollusks. Hundreds of millions of people rely on reef fisheries for protein. Tourism economies built around reefs collapse. Shoreline protection disappears. The cascading effects propagate through the entire marine food web. Larval fish depend on specific pH ranges. Shellfish can't form shells properly. Organisms at the base of the food chain fail first. Everything above them starves. This isn't speculation. It's chemistry. You can't negotiate with carbonic acid formation. You can't compromise with pH levels. The ocean responds to atmospheric CO2 according to physical laws that don't care about economic systems or political considerations. Nuclear war represents the most immediate anthropogenic threat to habitability. Not because of the explosions themselves. Those would be devastating locally but wouldn't threaten the species. The real danger comes from what happens after. Urban firestorms inject massive amounts of soot into the stratosphere. Unlike lower atmosphere particles that rain out quickly, stratospheric soot can persist for years. It blocks sunlight globally. Temperatures plummet. Agriculture collapses. Recent modeling of a full-scale exchange between nuclear powers suggests global calorie production could drop 90% within a few years. 5 billion people dead from famine. Even a regional conflict between India and Pakistan could cut food production in half and cause 2 billion deaths. The nuclear winter scenario isn't hypothetical. We've observed the mechanism on smaller scales. Large volcanic eruptions inject sulfur into the stratosphere and cause measurable global cooling. The year without a summer in 1816 followed the Tambora eruption. Crop failures across the northern hemisphere. Widespread famine. That was from a single volcano. Nuclear war would be orders of magnitude worse. And unlike natural disasters, it's entirely under human control. The decision to make Earth uninhabitable for billions of people sits in secure facilities in half a dozen countries. Mistakes happen. Systems fail. Miscommunication occurs. We've had close calls before. The fact that we're still here is partly luck. Supervolcanic eruptions add another layer of background risk. Yellowstone gets most of the attention, but several other systems could produce civilization-threatening eruptions. The probability in any given century is low. The chances of a Yellowstone supereruption in the next few thousand years are exceedingly small. But low probability isn't zero probability. And if it happened while we're dealing with climate change, biodiversity loss, and geopolitical instability, the combined stress could push human systems past their breaking point. A Yellowstone-scale eruption would drop global temperatures by up to 4 degrees Celsius on average. 7 degrees across land. More than 10 degrees across central North America. That level of cooling for years to decades would devastate agriculture. Food storage systems would be overwhelmed within months. Supply chains would collapse. Billions would face starvation. Not because the eruption killed them directly, but because modern civilization depends on stable climate and functioning global trade. Here's what keeps coming back. Earth has been uninhabitable before. Multiple times. The planet doesn't care. It's a ball of rock with a thin film of life on the surface. When conditions become hostile, life either adapts, retreats to refuges, or goes extinct. Eventually conditions improve. New species emerge. The biosphere rebuilds. But rebuilding takes millions of years. The Permian extinction wiped out 96% of marine species. Recovery took 10 million years before ecosystems returned to pre-extinction complexity. 10 million years. That's longer than the entire history of the genus Homo. For individual species, for civilizations, for anything operating on timescales shorter than geological epochs, extinction is permanent. There's no coming back. No reset button. No second chance. We're the first species in Earth's history capable of understanding this. We can study the fossil record, model climate systems, project future scenarios. We know what's coming. We know what causes it. We know how to prevent the worst outcomes. And we're choosing not to. Not because the solutions don't exist. They do. Not because we lack the technology. We have it. Not because we can't afford it. The cost of prevention is a fraction of the cost of adaptation or collapse. We're not acting because our institutions, our economic systems, our political structures aren't designed to handle problems that unfold over decades and centuries. We're optimized for quarterly earnings, election cycles, immediate threats. Climate change is none of those things. It's slow, diffuse, and easy to ignore until it isn't. The gap between what we know and what we do has never been wider. Every major scientific body agrees on the basics. Every climate model points in the same direction. Every ecological assessment shows accelerating decline. The evidence isn't ambiguous. The trajectories aren't uncertain. We know where this leads. Whether Earth becomes uninhabitable again depends entirely on choices made in the next few decades. The physics is already in motion. The chemistry is already changing. But we still have agency over how far it goes and how fast it happens. The window is closing. Not in some distant future. Now. In the time it takes to read this sentence, another hectare of forest disappeared. Another ton of CO2 entered the atmosphere. Another species moved closer to extinction. Earth will survive regardless. It survived worse. In a few million years, none of this will matter to the planet. New ecosystems will emerge. Different species will fill empty niches. Life will continue in forms we can't imagine. But we won't be here to see it. Neither will most of what currently exists. That's the choice we're making. Not whether Earth remains habitable for something, but whether it remains habitable for us. The question was never whether Earth could become uninhabitable again. The question was always when, and by what mechanism. Natural processes guarantee this planet's habitability is temporary. Solar evolution will handle it eventually if nothing else does first. What we're really asking is whether we accelerate that timeline from billions of years to decades. Every system we've examined shares one characteristic. Thresholds exist. Cross them and you can't go back, not on timescales that matter to anything currently alive. Ice sheets that collapse don't rebuild in centuries. Forests that transition to savanna don't revert because you stopped cutting trees. Ocean chemistry that shifts toward acidity doesn't neutralize because emissions dropped. The changes persist. This creates an uncomfortable asymmetry. The damage accumulates slowly, almost imperceptibly, until suddenly it doesn't. The transition from stable to catastrophic can happen within years once tipping points activate. But reversing that damage, if it's even possible, requires millennia. We're operating in a system where it's easy to break things and nearly impossible to fix them. The geological record offers no comfort here. Earth has recovered from worse conditions than anything we could create. The Permian extinction eliminated 96% of marine species. Life came back. 10 million years later, ecosystems were thriving again. But 10 million years isn't a timeline human civilization can work with. We need stability measured in decades and centuries, not geological epochs. What makes our current trajectory particularly dangerous isn't any single threat. It's the convergence. Climate feedbacks activate while biodiversity collapses, while ocean chemistry shifts, while political systems strain under resource pressure. Each crisis amplifies the others. The combined stress pushes toward thresholds we can't accurately predict but definitely can't reverse. We've compressed changes that normally unfold over millennia into decades. Evolution can't keep pace. Ecosystems can't adapt. Species that might survive gradual climate shifts over thousands of years face conditions changing faster than their generation times allow. The result is extinction debt accumulating across the biosphere. Walking dead. Species functionally extinct but not yet physically gone. The path forward isn't mysterious. The physics is clear. The chemistry is established. The biological mechanisms are well understood. Reduce emissions. Protect remaining ecosystems. Stop destroying the systems that maintain habitability. The solutions exist. We're not facing a knowledge problem or a technology problem. We're facing a collective action problem on a planetary scale. Every fraction of a degree matters. Every percentage point of forest cover matters. Every year of delay makes the eventual reckoning more severe. The difference between catastrophic and merely terrible sits in decisions being made right now, by people who mostly won't live to see the full consequences of their choices. Earth will remain a planet regardless of what we do. Water will still flow, eventually. Clouds will still form. The rock will keep orbiting the sun. But whether it remains the kind of planet that supports complex civilization, that maintains the ecosystems humans evolved within, that provides the resources billions of people depend on, that's entirely up to us. The window hasn't closed yet. But it's closing. Fast. And once certain thresholds pass, the trajectory becomes locked in regardless of future actions. We're running an experiment with the only planet we have, using incomplete knowledge, on systems we only partially understand. The margins for error are shrinking with every passing year. What happens next isn't predetermined. It's a choice. One we're making collectively through action and inaction, through the systems we maintain and the changes we resist. Earth has been uninhabitable before. It will be again. The only question is whether we're the ones who make it happen, and whether we do it in time to witness the consequences ourselves.